Okay, so I've started the video here. Welcome everyone. So let me set things up here. Give me a minute for that. Okay, so I think we are ready to go. So we'll talk about a very fundamental problem in geometry, which is the closest pair problem. And we'll just look at the problem in 2D. So this is not an approximation algorithms class, but then a lot of the ideas here, such as the use of grids, use of randomization, will be very useful for designing various approximation algorithms. So that's the reason I'm introducing this topic. And in general, it's a very fundamental problem. And so there are some very nice ideas which will go into building the algorithm that we'll see today. Okay, so let's start off by defining the problem in case someone has not seen this before. So you're given n points in the plane, and you want to know which are the 2 points which are closest to each other. Just say Euclidean distance, right? So in this case, looks like these two will be the closest pair. A very simple definition. And now, so what's known? So a lot of you must have seen an n log n time algorithm for this problem. And that works via the popular divide and conquer paradigm. So I won't describe what the algorithm looks like, but at a high level, what happens is basically partition these n points into equal halves on the left and the right, and you recursively solve the problem. And after doing that, you have to do a clever merge step where you try to see if there is a closer pair such that one is on the left and one is on the right. And a careful analysis, careful implementation is needed to make sure it's n log n and not n log square n. So, but I'll not go into that in today's lecture. But one thing I should point out is when we are designing these algorithms, it's very important to specify the model of computation. What do I mean by that? We want to know what are the operations that can be performed by the computer. So for the algorithm, this n log n time algorithm, it works in what's called the comparison model. In the comparison model, what we do is we perform very simple operations such as greater than, less than, or equal to on the input points. So we won't do any fancy operations. We only do these simple operations on the input points, and that is enough to compute the closest pair. Okay, and it can be shown that this n log n time algorithm is optimal in this model. Optimal in this model. Okay, so that's what I had to say about the previous work, or at least the, okay, everything is previous work here. This is what I wanted to say about this problem in the comparison model. So in today's lecture, what do we want to do? What we want to do is we want to look at a more powerful model of computation, which is known as the unit cost RAM model. So this is more powerful model. Why is it more powerful? Because we can do one operation which is called the floor operation, floor, or the seal operation. We don't need a seal. Floor operation is enough for us. Floor operation in constant time. If you don't remember what the floor operation is, we'll see as the algorithm, we start describing it. Okay. Also, in the algorithm that we'll describe today, we'll use hashing, which was not used in the previous n log n time algorithms, and randomization as well. So as you can see, we'll be using a more powerful model of computation, we'll be using hashing, we'll be using randomization, and by using a combination of all of this, what do we want to prove? In today's class, we want to prove the following. The closest pair problem can be solved in order of n time. Well, that's optimal in expectation. Because we are using randomization, that's optimal, right? So in today's class, this is what we want to prove. We want to prove that this problem can be solved in order of n time, given the more powerful operations that we can perform, right? Okay, so let's get started. So let's start with some preliminaries. I'll go very slow on these preliminaries because some of these might look obvious, but let's go a little slow so that when we dive into the actual algorithmic details, these things should not bother us. Okay, so this algorithm actually brings out the power of using grids. Grids are a very simple idea. The power of grids. Okay. So consider a grid G alpha. Okay. What does that mean? It basically means, so that visually this is how it looks like. This is basically, I'm drawing a series of vertical lines such that, and then horizontal lines, such that the vertical lines are separated by distance of alpha. So all vertical lines are separated by distance of alpha, and all the horizontal lines are also separated by a distance of alpha. Very simple. So I'm taking the entire two-dimensional plane and I'm drawing this series of vertical lines and this series of horizontal lines. Of course, this is a very conceptual description. We won't actually store this on a computer because there'll be infinite number of vertical and horizontal lines. So let me just point that out. This is just a conceptual representation. This one here. Well, okay. And now let's define what's called a cell. It should be very obvious from the figure here, but just to make it clear, you take any two consecutive vertical lines, any two consecutive horizontal lines, and the region which is contained inside all four of them is one cell. Okay, so that defines what a cell is. Okay, so now what we'll do is we will represent each cell with a unique ID. cell with a unique ID. Okay, and how do we do that? Well, pick any point p equal to x comma y inside the cell. Any point. Then the pair of numbers let me use a different color for this. So here's where the floor operation has entered. I hope everyone remembers what the floor operation is. So then this pair of numbers is the unique ID of the cell. Okay, so then one thing you can notice is all the points in this cell will map to the same ID. Well, let's take an example. Okay, let's change the color. So let's say this has a x coordinate of 100, x coordinate of 110, this has x coordinate of 100, this is x coordinate. Let's assume alpha is 10, right? And now we have a point here, oops. Now we have a point here, 105, comma 96. Now if you perform this operation here, right? Okay, I think I should start and new page here. Let me just redraw the figure quickly here. All right, so I said, okay, alpha is 10. I said this is 100, this is 110, this is 90, this is 100. Picked a point here with 105 and 96. Now I want to just perform that simple operation there. The number that will be assigned to this cell, which will be (100, 90). So essentially what has happened is at this point is getting mapped to its lower left corner. So all the points in the cell get mapped to the lower left corner. That's why the unique ID. So all the points get I mean, they get a unique ID and they all map to the same ID. That's the more crucial point I'm making here. So this 100, 90 will be the ID associated with this cell. Okay. Okay, I'm sorry for any disturbance that happened there. As I said, this is still new to me. Okay, so now so this was all a conceptual description of the graph, right? So now the question is, how do you store this G alpha on a computer? How to store G alpha efficiently. That's the key word. Efficiently on a computer. Well, here goes the answer. So the first thing we'll do is, as I said, because these are infinite vertical and horizontal lines, you can't actually store them on a computer. So first thing that you do is you ignore cells which are empty. It means no points lie inside them. That kind of makes sense, right? Why do you want to store them? So just ignore them. So now for a non-empty cell, what do? Just look at all the points that lie inside that cell and just keep a linked list of them. That's it, very simple. Keep a linked list all the points lying inside. And so that is easy, very simple data structure. The final step is the following. For all the non-empty cells, just maintain a hash table. And this is possible because we are assigning a unique ID to every cell. So that's why all the work that I was showing before was to show that every cell will have a unique ID, and those are nice integers, right? So then, let me just write that down. Actually, I should take that back. They need not be integers because it depends on alpha. But the point is they have unique values, and that is good enough for our hashing. Finally, maintain a hash table of all the non-empty cells. Let me write down, this is possible since all the cells have a unique ID. And at this point of time, I should make clear one assumption. We'll assume that all the hash operations can be performed in order of one worst case time. And that's, yeah, but we won't get into the details of this. That's a topic on its own. So let's just assume that all hashing operations will take only constant worst case time. Good. So then, so essentially this is how the the entire representation of the data structure will look like, right? So you have these non-empty cells, cell 2, cell 3, whatever, blah, 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 blah. And now with each one of them, because these are non-empty, we'll keep a linked list of all the points which are there in that cell. And then for all of these cells, we'll construct a hash table on all these cells. Right? So this is how our, let me just write it down, high level representation of G alpha. Okay, so then we described whatever we needed to about this graph G alpha. Okay, so now with this preliminaries, now we can slowly start getting into the details of our algorithms. All right, so let's slowly get started. Algorithm. Okay, so remember, we have to find the closest pair of points in 2D. So let's start with a very simple observation, and it's a very simple lemma. So it will be called a packing argument. So these packing arguments are very common in geometry because you have these objects which you want to pack in, say, two-dimensional space, and you can't pack too many of them. That's how the usual arguments go. Okay, so what are we saying here? Let me write down the statement. Let P be a set of points inside a square. Note the word square. I represent a square like this. Square. And the side length of the square is alpha, which is Cp of P. Now, what does this notation Cp of P mean? Let me write that down, where Cp of P is the distance between the closest pair of points in P. Write it down. It's the distance between the closest pair of points in P. Okay. Then the claim is P is less than or equal to 4. Well, if you pay a little bit of attention, you can see why this statement is true. It's not very difficult to prove, but let me provide the details here. So what we mean here is, we mean that the side length of the square is not too large. The side length is the closest pair of points, right? So that basically means you cannot pack too many points inside the square. So let's make that more rigorous here. So let's look at this square. And what I'll do is, I'll partition this square into 4 smaller squares of equal size again. So this had side alpha Now this will have size alpha over 2, alpha over 2. So like this, I have partitioned the square into 4 equal halves. And now the claim is the following. Only one point of P can lie in the shaded small square. Why? Because if you look at the diameter of the shaded small square, it will be, and I mean this diameter. So inside this smaller square, these are the farthest pair of points, which, and the distance between them will be okay. So the farthest, so the distance, okay. So this distance will be at most alpha over root 2 by simple Pythagoras theorem. So now, because of that, we are saying at most one point of P can lie in the shaded small square. And that's it. So the same argument can be repeated for all the 4 squares, and therefore P is less than or equal to 4. And to exactly realize P equal to 4, you'll have to do the following. You'll have to take the square of alpha and put all the 4 points at the corners. I think that's the only way you can pack 4 points inside the square. Try to do anything else, you can't pack 4. Okay, so then this was the simple packing argument, which says if there's a small enough square, then there cannot be too many points inside it. And that will be very useful going forward. Okay, so now, instead of solving the original problem straight away, we'll first look at what's called a decision problem and try to come up with an efficient algorithm for that. And this is a very standard way of attacking algorithmic problems, where you first solve the decision problem and make use of that to solve the final problem. So let's see what the decision problem is in our case. Again, this will be a lemma, and I'll call it a decision lemma. And what's the decision we have to make here? Let me write it down. So we are given P. P is a set of n points. I'll repeat it again. Cp of P is the distance between the closest pair of points and alpha is a parameter given to us. Now report whether the closest pair of points is equal to alpha, or if the closest pair of points is greater than alpha, or if the closest pair of points in P is less than alpha. So we have, and how much time are we given? We have to do this in order of P time, okay, which is order of n time. right? So the problem is clear. So we are not solving the closest pair problem, right? All we want to know is, given a parameter alpha, is our closest pair, the distance between the closest pair, equal to it, greater than it, or less than it? It's a more relaxed problem we're trying to solve, right? So please be clear of that. Okay, I mean, if you directly solve the closest pair problem, then it can answer this decision lemma as well, but that beats the purpose. So we won't do that. So what's the key idea here behind the proof? Since we have been talking about the grid all this while, the idea is to use the grid G alpha, right? So I use the term alpha here because we want to build the grid with this parameter alpha that is given to us in this lemma. It's the same alpha, right? So we will use the grid. We'll use the grid and the previous lemma, which had the packing argument. We'll combine both of them to solve this decision lemma. So let's get started. How do we do that? So let's consider a sequence here of these endpoints, which is P1, P2, so on up to Pn. Well, the algorithm is insert one point after the other into grid G alpha, right? So we already have discussed about G alpha. So into that grid G alpha, just keep inserting one point after the other. And as we are doing that, keep track of these two things. Keep track of two things. If at any point of time any cell has more than 4 points, then actually we are done. Then stop the algorithm and report CP of P is, well, can you see why this is true? Because of the packing argument. So go back to the previous lemma and see. Because we are building the grid with parameter alpha, if there are more than 4 points, then we can confidently say that there is a pair of points in our set P whose distance is less than alpha. It's simply the packing argument. Okay, so till the time this happens, once this happens, we just stop the algorithm, right? So if the algorithm is running, we can assume, till the time the algorithm is running, assume less than or equal to 4 points in each cell. While the algorithm is running. Right? This should be pretty straightforward to see. Okay, so what's the next thing to take care of? Well, I'll need to go back to a new one. Okay, so the second thing to take care of is the following. Let me just write it down first. When a point pi gets inserted, we want to ask the following question. What's the question we want to ask? It's the following. Is there a pair pi comma pj such that distance between pi and pj is less than alpha? It's a very natural question to ask, and turns out this is very easy to do with our grid. All right, so let me just draw our grid here. Bunch of lines like this. And say our point P is here. Okay, so this point P lies inside the cell, which has been shown here. And now, because we've drawn a grid, parameter alpha, if there is any point Pj which has a distance less than alpha, it has to lie in one of these 9 cells. And the 9 cells which I'll be shading now. This should be very obvious, right? Because I'm just showing this point P and drawing a disk around it of radius alpha. And that cannot cross these 9 cells that are being shaded here. So I hope that is very clear. If you just think about it, it will get very clear, right? So if you want to answer this question, we just have to look at these 9 cells. That's it. And we'll get our answer. Okay, so let me write that down. Claim, excuse me, only have to look at the 9 cells shaded in black. Okay, and now remember we said within each cell there can be at most 4 points, right? So in total there will be only 36 points, right? The 9 cells and 4 points inside each of them at most. So at most 36 points that we have to compare P with, and that's enough to answer this question here, right? So again, let me just write that down. Since each cell has less than or equal to 4 points, in total we have 36 points to compare with Pi. And hence, it's a constant time operation, right? When we are theoreticians, we ignore constant factors, so we can boldly say this is a constant time operation. Good. So now, again, so if a pair pi comma pj with distance less than alpha is found, then stop the algorithm. Because we have found that, then because now we can say the closest pair is less than alpha. If this doesn't happen, then just keep continuing the process, right? You just keep inserting one point after the other, and just keep track of the two things that I mentioned here, right? The first thing is this: if there's any cell which contains more than 4 points, then stop. Else just keep inserting one point after the other. Just keep track of this one thing and this second thing here. Every time a point is inserted, just look at the 9 cells, including around it. Again, that's a constant time operation. And just keep doing this. And finally, what you do is the following. At the end of inserting all the endpoints, if no pair of this form, no pair with distance less than alpha is found, then report that closest pair of P is greater than alpha. Actually, if you see the algorithm, you can actually see that you can also detect if there's a point equal to alpha as well. I just said less than alpha, but actually you can say less than or equal to alpha. That's not something we have to worry much about. Okay, so we only spend constant time every time a point is inserted. Right? If you look at the algorithm, you're only spending constant time. So overall running time is order of n. Okay, and now let me spend some time trying to argue the correctness of the algorithm. Ideally, I would like to leave it as an exercise, but okay. This is a video conference, so I want to be sure I'm explaining it clearly. Okay, we'll divide it into 3 cases. First is assume there is a pair PI-PJ such that distance between PI comma PJ is less than alpha, right? So without loss of generality, the short form for that is this. Assume PJ gets inserted after PI. Well, nothing wrong in assuming that. Then what will happen is, then PI already exists in GI. Not GI, sorry, G alpha, when you're trying to insert PJ into the data structure, right? And Pj is being inserted. Well, what does that imply? It implies that by the description of our algorithm, excuse me for that. So because Pj is inserted after Pi, so when Pj is being inserted, the algorithm will detect this pair Pi and Pj. Will detect that the distance between Pi and Pj is less than alpha. And yeah. So what I'm trying to say here is that assume that, say this is the closest pair. I think I should have mentioned that. Say, yeah, let's say Pi Pj is the closest pair. So then this algorithm will actually detect it because, as I said, Pj comes later. So then you'll actually make a comparison between Pg and Pi, and you'll actually observe that there's a pair whose distance is less than alpha. Okay, so let's go to the other cases now. Well, suppose the closest pair of points is equal to alpha. So again, you can use the same argument as before. I won't repeat it, use the same argument as before. Now the final case is Cp of P is actually greater than alpha. Well, this comes for free. Well, if the algorithm cannot detect case 1 and case 2, then obviously you're in case 3. The algo did not detect case 1 or case 2, then obviously closest pair has to be at least alpha. And that finishes the proof. Okay, so this was a packing argument we made, and then we had to solve this decision lemma. So all we said is construct this grid G alpha, insert points one after the other. Anytime you see more than 4 points in a cell, then you have found out that the closest pair is less than alpha. And every time a point gets inserted, you want to ask this question. You want to look at all its neighboring points to see if there's a possible candidate it can pair up with distance less than alpha. And again, that only takes constant time, right? And I tried to give a correctness proof, but it would be good if you can just prove it yourself again. I'm not sure if I did a great job there, but if you spend enough time, you will be able to figure this out. Not that difficult. Okay, so now having proven this lemma, I have to make one very important remark. Let me state that. Before I forget it, I should state this. Right? Again, the previous setting of the lemma, consider a set P of points and the grid G alpha. Excuse me. Okay. Now, assume there's a point P such that if you ignore that point P, then the closest pair is at least alpha. But if you include this point, then the closest pair is less than alpha, right? So in some sense, this is a very critical point. So what we are saying is P is in some sense a critical point because it's going to alter the decision about the closest pair. Okay. And now if the following scenario happens, let P be the last point of P inserted into G alpha, right? Suppose this is the last point that gets inserted into G alpha, then the above lemma will guarantee that we'll actually find the closest pair of points because P will be one of the points which has to participate in the closest pair. And the way I've shown the algorithm works, it'll actually find the point Q which forms the closest pair with P as well, right? So okay, let me just go back. Yeah. Look at this figure here. If P was the last point that was inserted into G alpha, then it will actually find a point. It will actually find the closest pair because you're comparing it with all the possible candidate points which can form the closest pair with P. So let me just write that down. And the above lemma, or maybe I should say the decision lemma, will find the closest point in P minus P to P. Q be this point, then P comma Q is the closest pair in P. As I said, anyways, P has to participate in the closest pair and it's finding the point closest to it, which is Q, right? So this lemma actually not only solves the decision problem, the point I want to make is if this scenario happens, right, that the critical point, which we'll define more carefully later, the critical point happens to be the last guy entering into your G alpha, excuse me, then it'll actually find the closest pair as well. Good. So please keep in mind this remark because this will be useful as we start writing down the actual algorithms now. Okay, good. So now we have solved a decision problem. Let's pause for a minute. So typically, if you want to solve the original problem, given this decision problem, one might wonder that, okay, can we do some form of a binary search, right? Because this looks pretty similar to that, right? But turns out, I don't see how you can use a binary search here because when you're talking about alpha or you're talking about distances, right? You're talking about distances, and distances need not be bounded by, and these can be arbitrary numbers, right? They need not be bounded by n, right? So the number of binary searches you have to do could be infinite, right? Because typically when you do a binary search, you have n items on which you're doing a binary search, so you know the number of binary searches you'll do is log n, right? But here you're talking about real distances, so it's not clear how to do a binary search on them. But maybe one can do. But in any case, if you do use a binary search, you're just losing a log factor, and that's not something we want to do. Okay, so now time to solve the original problem. Back to the original problem. Okay, so you want to describe this original problem. First, we'll start with a slow algorithm and then finally come up with the last algorithm. So let's start. I'll call this a slow algorithm. Okay, again, the idea is, because you've talked about this decision lemma and this grid, so we'll make extensive use of that. So we have to make a clever use of that to solve our original problem. Okay, so then what we do is, let's start. Excuse me. So we have this point set, and we'll consider an arbitrary sequence of these endpoints, right? Let me say it again. It's an arbitrary sequence. Okay. And now the high level idea is the following. So first is the base case, where you just look at the first 2 points in the sequence, just compute what their distance is, and then set that to alpha 2. Okay, let me just introduce some notation here. Right, that will be useful here. So let me just do that. So I want to say that, so keep in mind this notation because it will be useful going forward. So Pi will be the set of first I points in the sequence. Well, I should be more, this Pi look the same. So what should I do? Should be more careful while writing this. These are small ones. These are small Pi's. Try to write them very small. So this is really capital Pi, right? So capital Pi is basically the first I points in the sequence, right? And alpha I will be the closest pair of capital Pi. Okay. So the idea is the following, right? So let me, before even talking about the high level algorithm, just give you a flavor of how the algorithm will proceed. So the idea is, you have this arbitrary sequence. So the algorithm will insert one point after the other. And after inserting I points, you'll have this set Pi, right? And by that time, you'll always maintain an invariant. Okay. Let me just write it down actually. That'll help. after I rounds, the closest pair of Pi will be maintained or computed, whatever is the right word. Hence, alpha I is also known. Right, so the idea is you keep inserting one point after the other. So you'll have some Pi at a certain point of time. So you will incrementally keep maintaining the closest pair of points, right? Okay, it's kind of an incremental algorithm. Okay, so what's the first? So let me present some more details now. Not the idea, but actual details of the algorithm now. So as I said, the base case is the following, that you just look at the first 2 points in the sequence and find out what their distance is. And to maintain the invariant, you know what the closest pair is. It's just these 2 pair of points, and you know their distance as well, which is alpha 2. Now for the remaining points, I equal to 3, 4, so on up to n, perform the following 2 steps. So what we will do is, again, so we'll maintain this lemma that we had, right? The decision lemma. So we'll maintain that decision lemma on the points that we have looked at till now. So before the ith point is processed, we have looked at Pi minus 1, right? Okay, this is a set we have looked at. So the smaller points. So before the ith point got inserted, these were the points that we processed, and we know alpha I minus 1 as well. So we will assume that the decision lemma has been built on Pi minus 1 and G alpha minus 1. So we'll assume there's a grid with parameter alpha I minus 1, and all the points in Pi minus 1 have been inserted into it. Okay. So now when this ith point is being processed in this for loop, then first step is we insert Pi into the current decision lemma. Decision lemma data structure, which is nothing but this. Just insert this point Pi. And now if alpha I is less than alpha I minus 1, then you'll have to rebuild this decision lemma. Now that's the crucial part here. And you inserted this point Pi, and now because of this Pi, the closest pair has changed among the first I points, and that is alpha I. Now that has changed, so now you'll have to rebuild the decision lemma data structure. Okay, then rebuild the decision lemma data structure on pi. This time I have to build it on pi and g alpha I. So you have to change the alpha value this time. It was alpha I minus 1 previously. Now because the closest pair has changed, you have to build this time on g alpha I. Okay. So that's the algorithm. So at the end of this algorithm, what will happen, right? What will happen is the end of the algorithm, because of the invariant that I mentioned here, let me go there. It says after, yeah, we are incrementally maintaining the closest pair, right? So the correctness is guaranteed by that. So at the end of the algorithm, we will know alpha of n and the closest pair of points, because we are maintaining that invariant. Okay, so now let's see. Let me go back here and write down something here. If alpha, here I said, if alpha I is less than alpha I minus 1, if alpha is equal to alpha I minus 1, then do nothing. Right? Let me just. So in some sense, this is the good case, because when this happens, then the closest pair has not changed. And so you can use the same data structure, the same grid, the same data structure for the next iteration. However, if this happens, that's the bad case. This is a bad case because this point Pi that you inserted participated in the, is part of the closest pair in the first I points. And based on the remark that I mentioned before, you can go back to that. This remark that I said, if P is the last point that is inserted till now, and that is the one which is flipping the value. I mean, without it, the closest pair was something, and because of that, it flipped, right? That's what is happening here. So the closest pair was alpha I minus 1 before it got inserted. But once it got inserted, the closest pair became less than alpha I minus 1. Right? So when that happens, then you can actually find the closest pair. That's what this remark is saying. So you can actually, so when this case happens, case B, then you can actually find the closest pair. And because you can find the closest pair, you can compute alpha I as well. Right? So let me just write that down. When case B happens, then the closest pair in Pi is reported, and hence alpha I as well. Okay. So how much time does this algorithm take? Right? So if only good cases happen, then this algorithm will run very fast. However, if only bad case happens, which can happen, right? Which can actually happen every time. It could happen that every time you insert a point, if you're very unlucky, the sequence that you have of points P1 to Pn is so bad that every time you insert a point, that point participates in the closest pair till now. Then you'll always fall in the bad case. And the running time will be pretty bad. So worst case running time will be the following. That you have to rebuild the grid each time. And every time you have to rebuild the grid, there are I points in it. Rebuild the grid / decision lemma structure. So every time you have to rebuild, there are I points in your data set till then. I mean, I points, the set Pi. So you have to rebuild based on that. So if you do this summation, this will be order of n squared, and that is very bad, right? Okay, so then what was the whole point of doing all of this? We already had an n log n time algorithm. And then we are saying if we are very unlucky, this whole grids and all these things that we are doing can actually lead us to an order of n square algorithm. So that's pretty bad. So let me ask you a question at this point of time. So this is an exercise, right? So please try to solve this exercise. It's a very simple exercise. Just draw an instance of points which can lead to order of n square running time of the algorithm, of this algorithm. Very simple exercise, but just so that you can actually visualize, right? Just draw an instance of n points which can lead to order of n square running time of this algorithm. And in what sequence should these n points be inserted? Okay. So now, the promise that I made at the beginning of this lecture was that we'll look at an order of n time algorithm for the closest pair problem, right? So I have to fulfill that promise. So there's one more trick that has to be applied. Once we use this trick, then we are in good shape, right? So linear time algorithm is what we are aiming for, right? So there was one trick which we have not used till now, and that is randomization. It's a very powerful idea, especially in this context, because we said our sequence of points, right? The sequence P1 to Pn could be very bad, right? Because the bad case can happen every time. So a good way to avoid that is to actually perform a random permutation of all the endpoints, right? And now insert points in that order. So the algorithm is exactly the same as before. Nothing changes. The only change is the first step. You perform a random permutation of the points and now insert them in that order. And now we will claim that the bad case will happen rarely, or it will not happen that often. Okay, so that's it. That's the algorithm. The key part is the analysis, right? So let me write that down. The algorithm is the same as before. The only change is that we perform a random permutation of P. And insert points in that order. That's it. Okay, so now let's do the analysis. The algorithm is clear, right? So now let's do the analysis. So we'll prove two lemmas. I can directly prove the second lemma, but I think proving these two lemmas would be a better way of appreciating what's going on. Give me a second to write down the lemma. Let T be the number of unique values in the sequence alpha 2, alpha 3. So I hope you remember the definition of these alphas. It's the alpha I is the closest pair of points, the distance between the closest pair of points in the first I points. Then expected value of T, right? So this definition means expected value of T will be order of log n. So in other words, in expectation, the number of times the grid is rebuilt is order of log n. Previously we said if your sequence is very bad, the grid can be rebuilt each time, which is n. But now because of this random permutation that we are doing, in expectation, we won't rebuild the grid too many times. It's actually order of log n. Okay, so let's do the proof as well. Well, it's a very nice proof. It's one of the reasons, this lemma is one of the reasons that I'm discussing this topic today. Okay, so let's introduce some notation. So for the first 2 points, anyways, we just compute, we don't build the grid, we just find out their closest, the distance, and that's enough. It's from the third point that gets inserted that the grid is needed, right? And the decision lemma structure is needed. For I greater than or equal to 3, let xi be an indicator variable, that is equal to 1 if and only if alpha of I is less than or equal to alpha I minus 1. It means whenever a grid has to be rebuilt, then this condition will happen. Then we'll set xi equal to 1. Right? So then by definition of the indicator random variable, expected value of xi is equal to probability of xi equal to 1. Right? Also, t will be equal to exactly this quantity. Right? Okay. So now we want to bound this quantity probability xi equal to 1, which is nothing but probability that alpha I is less than alpha I minus 1. So to bound this, consider the point set pi. And we make this following important observation about pi. Pi is a, so initially we took this set P and we did a random permutation of it, right? But if you just focus on pi, just pi, right? We can make the following statement. And this is very important. We say that pi is a random permutation by itself. What does that mean? It means it is a random permutation of the points P1 up to Pi. Okay, this was capital P, these are small p's. Right, so all we are saying is you just fix these I points, P1 to Pi. Within themselves, they're again a random permutation. Right, so that's a simple observation, but a very important observation. Okay, so now comes the definition of critical points. Right? A point, so again we are focusing on this points at Pi, capital Pi. Point Q in capital Pi is critical if closest pair of Pi minus Q is greater than closest pair of Pi. I think I should write it again because it's an important definition. So we spoke about this before, but let's make it very precise now. So without this point Q, this was the closest pair distance, the term on the left hand side. And now because of adding this point Q, the closest pair actually comes down. The distance of the closest pair actually comes down, right? So then Q will be called a critical point. Okay, so now the question I want to ask is, how many critical points can there be? Let me point out a few examples here. If there's a unique closest pair, if there is a unique closest pair, then two critical points. Well, that should be obvious, right? If there are other interesting cases, if there are more than one closest pairs. Well, can that happen? Yes. Turns out it can happen. When you could have a pair like this, another pair like this, both have equal distance between them. Then if you look at this definition, then zero critical points. Again, think about it. Just go through this definition and look at this scenario. It turns out none of the points can be critical points. Okay, so I'll not give you all the details. Now, let me give you an exercise. Again, this will be an exercise, so please try to solve this. It can also happen that there is exactly one critical point. When will that happen? Please try to think about this. Good exercise. Right? So we said there could be two critical points, there could be zero critical points. Turns out there could be exactly one critical point as well. Right? So think about that. So let me pose one more exercise here. Again, I can prove this, but I'll leave it as an exercise because that will give you, it'll force you to understand this problem better. Exercise. Prove that there cannot be more than two critical points. So I'm saying there can be zero critical points, one critical point, two critical points, but not more than that. But that needs a formal proof, and I'll leave that as an exercise. A very simple exercise. Right? So I've defined what a critical point is, and this is what I have to say about it. Right? And now remember that we are saying PI is a random permutation. Right? So assume there are two critical points. in pi, right? And now the claim is probability that xi will be equal to 1 is equal to 2 over I. And why is that? Let's show this pictorially. So we have this I points here, and we are saying 2 among them are critical points. Right? And what did we do with these I points? We've created a random permutation of them. Right? So our PI is basically a random permutation. And we want one of these critical points to land in the end. Right? Only when it lands in the end will xi be equal to 1. Right? Then xi is equal to 1. Because when one of the critical points lands in the end, then that will make the alpha value change. There was some alpha value going on till then, alpha I minus 1. If this critical point lies in the end, then the new alpha I will be smaller than alpha I minus 1, right? And what's the probability that one of these two will come in the end? It's exactly 2 over I, right? Okay. Now there was one more case. There is one critical point. Well, again, by the same argument, probability xi equal to 1 will be 1 over I, because there's only one critical point this time, right? So overall, it's safe to claim that probability of xi equal to 1 will be bounded by 2 over I, right? Okay, so remember this equation. It's a very nice equation because it says as the point size increases, right, the probability of the grid being rebuilt gets smaller and smaller, right? Say I is n. So then it says in the end for a grid rebuild to happen is just 2 over n, which is a very small probability, right? And that's where we save the time. Okay, but before getting there, the goal of this lemma was to compute how many times will the grid be rebuilt, right? So by linearity of expectations, let's finish that. Expected value of t is equal to expected value of this. These are now a bunch of standard calculations, so I'll just go through them very quickly. Very routine. This we have already shown is 2 over I, and now there's a very standard inequality, the harmonic series. This gets, and we are done with the proof. So the idea was, the key ideas were two, that it's a random permutation among the points of pi and the definition of critical points. You have to combine these two and you're done. Okay, so now you're not yet done because again, if we naively use this above lemma, then the running time is still n log n, right? Naive use of the above lemma. Then running time is order of n times order of log n is equal to n log n. But again, that's not useful because we already have an n log n time algorithm. But as I pointed out, let me go back there. So look at this equation at the bottom, right? Bottom corner. So we still not use the fact that initially there could be a lot of rebuilds that can happen, right? But then those rebuilds won't be very costly because the I value is very small. But then as the algorithm proceeds, the I value increases, so the probability of rebuilding becomes very less. So even though it might be costly, but it'll happen very often. So we'll exactly use that idea, do a more careful analysis, and we'll be done. So we're almost there. Just hang in there. One final piece of lemma, which is again very technical. Not all the ideas that had to be put out have been put out. We just have to prove one final theorem, the final theorem, and we'll be done. So please hang in there for a few more minutes. We've reached the end. Okay, here we go. For a set E of n points in the plane, we can compute the closest pair of P in order of n expected time. So just like before, let xi be the indicator variable which is 1 if alpha I is not equal to alpha I minus 1, otherwise 0. The running time now runtime is proportional to, so I want to avoid having to write down the big O symbols and all, so I'll just say running time is proportional to this. Okay, so how should we understand this? Let's assume that the grid rebuild didn't happen in the ith iteration. If it didn't happen, then xi is 0, which means you spend constant time to perform that particular insertion, which is what we know, right? However, if the grid rebuild happens, which means alpha I is not equal to alpha I minus 1, then xi is 1. So then it takes order of I time to rebuild the whole grid, right? So this running time is exactly capturing them, right? Depending on the value of xi, that's the time taken in each iteration, right? So now just do a bunch of perform the expected running time analysis. The expected running time is proportional to this. Nothing much happened there, and this will be just okay, I'm doing a bit of loose analysis here, but I hope you get the point by this point of time. So expected value of xi is going to indicate random variable. It's just probability of xi equal to 1. So maybe I can make this 2n, I guess, if I understand it correctly. Maybe it's n or 2n, doesn't matter much. Yeah, maybe 2n, but that's okay. Well, okay, so now we've already have a good upper bound on this. So let's just plug that in. And this is the most interesting part of this lemma, then not theorem actually. So let me write that down in red color because this is the most beautiful part of the equation then. And this becomes 4n. And that's it, we are done, right? So exactly the point I mentioned, right? And this is the crux of the algorithm, this part here. That the grid rebuilding could be very costly, but then the probability of that happening is also very less, right? 2 over I. Because of that, in expectation, every iteration takes only constant time. So overall, the running time will be order of n. Okay, so with that, I've actually shown you, let me see, it's a pretty detailed description, but I thought I should go as slow as possible because it's an online lecture. You don't get to ask questions in real time. So I had to go very slow. Sorry about that. So let's quickly recap, right, what happened. So we said we wanted to solve this closest pair problem in the more powerful model of computation, right? And we wanted to use hashing, we wanted to use randomization. Using all these operations, we wanted to say that we can actually solve this problem order of n time. So then we introduced this notion of grids, right? And it's a very simple idea. We showed a simple way to represent them in a data structure and said that all these standard operations can be done in constant time. And then we said there's this packing argument which says it's a small enough square, then you cannot pack too many points inside it, right? And things really started happening from this decision lemma where we had to solve the simpler problem of knowing whether the closest pair of points is less than a given parameter alpha or it's greater than that. For that, we had to use this idea of grid, insert points one after the other. Right? And every time you insert a point, you only do a constant time operation. Right? In step 1 or step 2, you're always performing a constant time operation, and you're always trying to find if there's a pair pi pj whose distance is less than alpha. Once you find such a point, you report it. And if you don't happen to find such a point, then you just claim that the closest pair was greater than alpha. And I tried to show a proof of correctness, but it would be good if you can go through it on your own. Right? And then we said, if P is the critical point, right? That's the one that's flipping the value of the closest pair. And if that's the last point being inserted, then the above algorithm will actually give you the closest pair of points. And that's useful when you actually describe the algorithms. Then we went back to the original problem. Initially we said, okay, we'll consider an arbitrary sequence of the points and insert them one after the other. And always we'll maintain this invariant that based on the points which have been inserted till now, we'll find the closest pair. Closest pair of the points inserted till now. Right? And we did this using grids. By that I mean the decision lemma data structure was being used to keep track of the points being inserted till now. And in that process, you had to rebuild the grid many times. So then we said, if this is an arbitrary sequence, then things can get very bad. You might have to rebuild it many times. That gives you order of n squared. And then finally we said, the cure for all this problem is randomization. The same algorithm, but now insert the points in a random order. And then we said, then that the grid will change only log n times, not more than that. And in fact, if we are more careful in our running time analysis, then in expectation, in every iteration, the expected time of every iteration is only constant. And hence the entire running time will actually be just order of n. Any final comments? Well, the only final comment is extends naturally to higher dimensions. I'll again leave that as an exercise for you to figure out how to extend these ideas to higher dimensions. Okay, so I think I have spoken enough about this problem. I think I should finish right here. Thanks a lot.